Welcome back. So today we would be starting back on convolutional neural networks. So in the last class I had introduced you to some of the very basic operators on convolutions and some of the basic structural building blocks for how a CNN works. Today we would be building up on top of what we had done in the last class and get you introduced into one of the early versions of a convolutional neural network, which was referred to as a LeNet. It is still referred to as a LeNet and attributed to Jan LeNet, who had invented this particular one. And we have already solved a few examples in our autoencoder tutorials using the MNIST digits classification problem. So LeNet was technically a thing which was invented more of from the MNIST perspective, and it was for the standard NIST database, which had the challenge of identifying 26 alphabets in the English alphabet corpus in the uppercase, lowercase, making it 52 such things to be identified, and on top of it 10 different numbers, and that together makes it a 62 class classification problem which was being solved. So that wasn't a small problem as such, but the shorter version of that and the simpler and sweeter version is what is done with the digits identification, since each digit is quite uniquely available and has a major implication in a very practical sphere of life, and that's on postal code identification. So without much of a delay, let's get started into what we are doing. So today we would be working on convolutional neural network and taking down this example of LeNet over there. I would be revising a few of basic concepts which we had covered down, and also coming down to a bit of numerical solution, so that it makes it easier for you to understand and grasp the concepts as well. So this is organized as we'll just be revising the building blocks, some of these building blocks which are important in the perspective of understanding LeNet, and then I would be showing down what is the standard LeNet architecture for handwritten digits classification. So let's get into it. So if you remember convolution, how it went down was that if you have an image which has a width of m and a height of n and 3 channels, then you have a 3 cross m cross n. If this is a grayscale image, then it becomes 1 cross m cross n. Okay. Now the point was that we can define one kernel which will have 3 different planes or 3 different channels of the kernel as well. So this can be a 3 cross 3 kernel or a small m cross small n kernel, and the number of channels over here, since we are doing 2D convolution, so that will match down to the number of channels in the image space as well. So this becomes one kernel. Now as I convolve with this kernel of 3 cross w cross h, then I am going to get down one matrix over here. Now similarly I can have another kernel, and then as I convolve with this one, I get down another matrix coming down over here, and this output matrix over here will have dimensionally t equal to, so the first dimension, which is by number of channels, which comes down by default definition, that is equal to 2 or the number of kernels present over there, and the width over there is m minus w plus 1, and height or the number of rows is n minus h plus 1. So this goes down pretty much by our standard definition of convolution. So now when we were trying to do a convolution with the stride and padding, which is a very practical case of working it out, the idea was that if you have some image over there and your if you are trying to do down your convolution by just moving it out, then the major problem which comes down is at the borders you will not be able to operate. So the size keeps on decreasing from the periphery of the image itself, even if you are taking it with a stride of 1. And in order to get rid of that, what we had done was that our idea was, let's pad it down with zeros, which is equal to this extra number of points which just get outside in case we want to have a full sized convolution result also coming down. So if I have a pad height of ph and a pad width of pw, and then we start convolving this one with a stride of s, and appropriately it keeps on merging and then comes down. So as it happens together, so this is how a resultant matrix is formed over there, and then your output has a width of OW, which is equal to m minus w plus 2 pw divided by sw, where sw is the stride along the width, w is the width of the convolution kernel, pw is the pad applied along the dimension of width. So each side you will be having pw and pw number of zeros padded down, so that makes it 2 pw, and m is the original size of the image before padding. So after padding, the size of the image becomes m plus 2 pw basically. So and similarly for your height, you have this sort of a relationship as well coming down. So that's how your final modified thing comes into it. Now the point is, let's get into a practical demonstration of how it works down. So I am using this example from a well-known course material from Stanford, and I chose to, instead of redrawing the whole thing, I just chose to actually show it to you using just this animation over here, keeping in mind that this is one of the best animations to ever be able to understand it. So let's get into how it works out. So you see these grays over here, and these grays are all the zero padded ones, and this ones in the blue, this is the one which is a size of the original image itself. So this is the matrix part of the original image. Now my point is that I want a 3x3 convolution kernel to convolve around this image. So this side, if you look into it, this is my input image side over there. Okay, so these guys write it down in a convention of 7x7x3, where 3 is the number of channels. So this is my first channel, this is my second channel, and this is my third channel. So as in with the RGB image, you have 3 channels. So here I get the same thing coming down as well. Now that I have these ones, the next point is that I need to have a convolution kernel over here, and they also take down 2 different kernels. One of them is W0, the other one is W1. Now W0 has a 3x3x3 form, which means that it has a spatial span of 3x3, and there are 3 such channels over there. So the first channel corresponds to this first channel of the image, the second channel of the kernel corresponds to the second channel, and third channel corresponds to the third channel. So now if you see down, these are some arbitrary weights associated over here for the convolution kernel. So this is on the first channel of the first convolution kernel, this is on the second channel of the first convolution kernel, this is on the third channel of the first convolution kernel, and on top of that you have a bias as well, which is associated with each of these channels. So the first channel will have a bias of its own, the second channel has a bias of its own. Now when say it was starting to operate on this one, then yeah, it does get a bit annoying at times that it keeps on moving while I am referring to. So if you look into this animation, so the first channel of the kernel operates on the first channel of the image itself. Okay, the second channel of the kernel operates on the second channel of the image, the third channel of the kernel operates over here. Now accordingly, these W0s, they will give an output of O channel 0. So when you see this one operating over here, the total output is what is coming down on this channel. When you see this move down and go to this one, the output keeps on coming on this channel over here, and that's how it operates. So by our definition, we had that the weight is multiplied by this one. So here when I put down a 3x3 matrix over here with this one, then I get a 0 into 0 is a 0, again a 0 into 0 is a 0, minus 1 into 0 is a minus 1, that is the first non-zero, minus 1 into 0 is again a 0. Okay, this 0 into minus 1 is a 0, this 0 into minus 1 is a 0. Now this 1 times a 0 is 0, 0 times a 0 is 0, this minus 1 over here is what corresponds to this 1 over here, and that becomes as minus 1, and this 1 and 1 dot product will give it to a value of 1. So I have a minus 1 plus 1, which makes it 0. I do the same thing over here. So over here when I am doing the same thing, these 4 elements over here are all multiplied by these 5 elements are multiplied by 0. So you don't have an resultant option. This 0 and this 2 will correspond. So this 0 into this 2 makes it a 0. This minus 1 corresponds to this 1. So there is a minus 1. Then there is a 2, and then there is a 1. So this effective result from this channel's multiplication is 2. Okay. So I have a 0 from here and a 2 from here, that makes it 2. And now I take this particular kernel, I have all of these zeros with these elements over here. So these 5 elements don't give me any result. Now 1 into 1 makes it 1, minus 1 into 0 is a 0. Then 0 into 1 is a 0, minus 1 into 0 is a 0. So the only result over here is a 1. So I have a 2 plus 1, and then I take another 1 over here, which is my bias. So 2 plus 1 makes it 4, and that's the resultant value which comes down over here. So you get down the point that it's very much a volume which is getting convolved, and that's the resultant which you get down over here. Similarly, you can keep on doing for all other locations, and you would see this one appropriately populated. You repeat the same thing for the second kernel, and then you would be getting down the second channel of my output coming down. But remember that the bias for the second kernel is what is present over here, and each kernel has its own bias, and that goes down pretty much with the yeah. So this was an easy option of stopping it, which I overlooked. So if like we can go down to at any position. So yeah, say this is the second position where I am located at. So now you have stopped it down. So now you can again take the same kind of a multiplicative product, sum all of the dot products, add down the bias, and you will be getting this value of 5 over there. Now keeping one thing in mind, that this is how a standard convolution would work. Now if you keep on repeating, say these two outputs over here, the two output channels, and then they are also exposed to some sort of a convolution, then you would have the same thing repeating over and over again, and then that's a pretty standard way in which this would be going on. So with that, let's get back into our convolutions as well. So this is what we finished off discussing. So that's how it was getting filled up completely, and you had your height and width. The next part was on understanding pooling operators, and this pooling was basically a way of reducing the size of an image. So the whole concept which I said was that there can be an option in which I would like to reduce this image size to half of it. Okay. So the point is that if I have a 4 cross 4, then if I am reducing it on each dimensions to half of it, it becomes 1/4 of the total area and gets converted into a 2 cross 2 matrix over there. And this is how it would keep on repeating itself. Now this pooling can be done in terms of something called as a max pooling, in which what I would do is I would take down the maximum value and then place it in the middle over there, or this can also be done in terms of an average pooling, in which the idea is that in this 2 cross 2 matrix I will take what is the average value and just resubstitute it over there in my pooling layer over. Now if I want to do pooling, the earlier case was where I was using a stride of 2 to pool. So that meant that my stride is equal to my width or height of the pooling kernel which I am using. Instead of that, I can even choose to do continuous stride, and that makes it an interesting proposition over here. So technically what this means is that if I have some sort of an average pooling going down over here, so that's equal to some form which comes down over here, and this is my relationship between my width and height, and this effectively gives me basically a grayscale dilated version of the whole image which comes down. So you can see quite amount of similarity between what is happening down at certain number of operators in convolutional neural networks to your standard operators in case of a image processing based solution in a standard classical computer vision based approach, and these are the ones which work out. So with that, let's get into what's called as a LeNet. So if you go by the standard definition, this is the architecture which I have directly taken down from the author's paper, and I give full citation to them. I have not redrawn the whole thing, because this is from a tutorial perspective, this is possibly the best rendering which we have for LeNet available. Now the whole concept over here is that you take an image of 32 cross 32, and this is a grayscale image. Okay. So although we were doing our experiments on 28 cross 28, and the whole thing was basically by reducing 4 peripheral pixels over here to get it down into a 28 cross 28, and then that's something which matches down these feature maps over here. But for reasons not quite well known to most of us, we actually don't know what happened to this original which was proposed on a 32 cross 32, and while the actual data which is available today is a 28 cross 28. Now how this goes on over here is that the first idea is take a convolution from this 32 cross 32, and then this produces a feature map of 6 channels over here, 1 2 3 4 5 6, which you see over here as the number 6 in C1 feature maps, and then the size XY size is 28 cross 28. Now from there, the next point is that we do a max pooling and convert it to 14 cross 14. That means that there is a 2 cross 2 and a stride of 2 max pooling which is applied, and since there are 6 number of channels, the same number of channels get preserved over there. The next one is with C3, which is the next convolution. So this 1 2 3, this is the layers along the depth, and C's are for convolution layers, S are for subsampling layers, which the authors have themselves kept on defining. So the next one is from a 14 cross 14, you go down to a 10 cross 10 and 16 such maps over there. From the 16 you do a subsampling, you come down to a 5 cross 5 size from a 10 cross 10, so that's also a 2 cross 2 subsampling, and then you have 16 of these. So you have 16 into 25 number of neurons in total. So 16 into 25 would make it basically 400 neurons. Now from 400 neurons you map it down through a fully connected layer to 120 neurons, which is C5. From there it maps down to a fully connected network with 84 neurons. From there it maps down to a fully connected network with 10 neurons, and over here what is called as a Gaussian connection is basically a sigmoid transfer function. Now with this kind of a sigmoid transfer function you can actually stretch down your values in the range of 0 to 1. So typically, since this is a digits classification problem, over here on the output side there is a 10 cross 1 neuron bank, and this is a 1 hot neuron. So any one of these neurons is going to be 1, the rest of the neurons are going to be 0. So we have a convention actually of writing this one, and the idea of writing this one is something of this sort. So if we try to write down a convolution, we would try to express it in something of this form. So 6C means the number of channels in the output which we need to produce, and that will basically define the number of such convolution kernels which I need to have within my convolution operator. 5W over here means I am using a 5 cross 5 kernel size. So this is width of the convolution kernel which I am using, and for simplicity we try to use square kernels, which means that the width and the height are same. There are possibilities of using say rectangular kernels as well, and within your coding exercises you would see that we always put down, and so when we start down with the convolutional ones you would see that we put down 2 dimensions over there. So the first dimension is the width and the second dimension is the height of the kernel. Now there is pretty much an option that you can put both of them the same, which works out pretty much for natural images, but then there are certain sort of images in say which are non-linearly sampled. So your x sampling along the x direction and sampling along the y direction is pretty different. In that case you would more of prefer to put down 2 different kernel dimensions. So your width of the kernel would be very much different from the height of the kernel. Now here what I do is I take a stride of 1 and then a padding of 0. Now one question comes down is, I have already written this one down for you, but can you actually, given this information over here, can you actually find it out? So that's a very pretty exercise question which you can a lot of time expect. So it's not just from a examination point of view that you would be asked this question over there, but then most of the authors and most of these publications which have these convolutional neural networks, they would just be drawing out the network to you. They would give down dimensions of the results at each of these layers, but most of the time not even speak about what was the kind of the convolution operator which was used over there. And now you have to figure out from your side that what can be an optimal combination of these convolution kernels which were typically used. So we generally start by a configuration whereby we take down the minimum size of the convolution kernel, and here the idea was that if we go down by the concept of a minimum size of the convolution kernel, then let's see what comes down. So you see that the size was decreased on both the sides by a dimension of 4. Now if that has to work out, one option may be that I don't put down a padding over there and then I take a 5 cross 5 and take a stride of 1, and that pretty much fits down within this kind of a constraint. Yes, you can have other convolution options as well, and pretty much I would say that please try them out as well to see which other sort of a combination, but 6C anyways will remain constant because your output over here has 6 channels unlike anything else, and that's pretty much something which defines the number of channels over here. So similarly, let's look into this subsampling over here. Now the subsampling, if you see, so it was going down by a factor of 2 on both the sides, so that and the number of channels will be preserved because that does not have any impact on subsampling. So this would mean that I have some sort of a 2 cross 2 kernel and a stride of 2 employed over there. So this subsampling layer over there, or the max pooling, is with a 2W2S. Okay. The next one is again a convolution which produces 16 channels output. We again use a padding of 5, a width of 5 kernel over here, a stride of 1 and a 0 padding over there, and that technically brings down 14 cross 14 channels, 14 cross 14 sized output to a 10 cross 10 sized output. So remember it was W minus, so your this dimension M minus W, which was the width of the kernel, plus 1. So that makes it plus 2 PW obviously. Now your pad over here is 0, so that does not contribute. Your width over here is 5, so it becomes 14 minus 5 plus 1, and that makes it 10. Okay, and that divided by 2S, which was your stride over there, and the stride, since we are keeping so divided by SW, sorry, so SW was your stride, and since our stride is 1, so this whole division factor over there unifies, and then you get down your option. So similarly, the next sampling and the max pooling is of 2W 2S, and the whole network can accordingly be represented something like this, that you have your input which comes down. From your input you do a convolution with 6C 5W 1S 0P. Okay, from there you get into a max pooling with 2W 2S. From there you enter into a convolution with 16C 5W 1S 0P. From there again you have a max pooling of 2W 2S. From there you have a flattening. So this flattening is to get down 400 neurons which comes down over here. So you linearize and get down a flattened layer of 400 neurons. So which basically means that here you have 16 into 5 into 5, that's a 3D array in which it's available. Flattening is an operator which basically converts this 3D array which has 400 such points into one single one dimensional array. So it's a 400 cross 1 array which you have as of now, and that can be now connected down to your fully connected layers. So there is no learnable parameter as such when you are flattening it out. It's just some sort of a indexed arrangement into one single 1D array. That 1D array can now be connected to 120 element array through a fully connected layer, and these weights over here are trainable weights. From 120 they go up to 84. These are again trainable weights. From 84 it goes again to the output. These are again trainable weights, and here you have a nonlinearity of a Gaussian connection. So this together defines my sort of connectivity throughout the whole network which I have now. So how it works and looks like is something of this sort. So I have taken down this from the direct website of LeNet, and you can actually get down much more details if you are there on this particular website of Jan Lekan. So this is from Jan Lekan's own website, and let's just zoom into that. So if you look over here, so he has a very good implementation of LeNet 5. So LeNet 5 comes down from the fact that you have total 5 number of layers over there. So if you recall back from our discussion over here, and we count down the number of layers, so there is 1 2 3 4, and then this whole part over here which becomes 5. Or another explanation is basically taking down the number of learnable parameters. So you have one convolution which has one learnable parameter 1, the second convolution which is a learnable parameter 2, because subsampling does not learn anything. So we have 2 layers which have 2 different learnable parameters. Then from here you get down to fully connected layers. So 1 2 3, there are 3 weights which you need to learn down over here. In total there are 5 different nonlinear transformations and learnable parameters through which this network works, and for that reason this is also called as a LeNet 5 layer. So here if you look into it, so he gives a intuitive explanation of layer 1. So this is basically the output which comes down from the first convolution result. So you remember that there were 6 such channels. So this is 1 2 3 4 5 6. So you have an image, this input going down over there, you convolve with 6 different kernels, and this is the output you see on each of these resultant over there. Now from there it goes on to layer 3. So layer 2 was basically a subsampling layer, so that made it half of this size. So from a 32 cross 32 it became 28 cross 28. From here it became 14 cross 14, and then we had 16 such combinations coming down. So you have 1 2 3 4, you can just count down, there are basically 16 such layers over there in layer 3, and then you had another subsampling which made it to 5 cross 5, and then we had a convolution rundown on that one as well, and this is the output of that. So there were total of 16 5 cross 5 channels which comes down over here. So this is the result which comes down. Now if you see in the initial you had an image, then you had some sort of edge oriented or accentuated versions of it, then we were getting down some sort of a sparse representation, and finally what you get down towards almost the end, which is your 400 neurons, is technically a bit stream. Now this bit stream is something which is important in terms of firing out your neurons to classify what is being seen over here, and that's how this result keeps on coming down. So what they do is that there is a running window kind of a thing. So you start from here, here, and then here, and you have 3 different detections being carried out, and that's what's being shown over here. Now if all the 3 detections when they populate and show the same number, you see that number also coming down over here as the answer. So this is based on a lot of papers and work which they had, and the earlier ones was what came down around in 1989, and since then it has been going on. So there have been a lot of advances put down onto this particular field, and till recently when we had the boom, so over a long period of time it was really hard to actually understand and create down these weights and create down a learnable aspect over there, and accordingly it took a lot of efforts for the community to grow up. But today that we have access to compute power and we have a good amount of access to libraries and making out easy prototypes for these methods, they are coming down into the forefront. So in the next lecture, we would actually be implementing LeNet 5 by ourselves, writing down our codes and doing it, and eventually from LeNet 5 we will be getting into understanding more and more details of how other convolutional neural networks work and what modifications can we do within that architecture. So what can be different kind of, so as of now we have just studied on the architecture, but you know that there are other aspects of cost functions, there are aspects of learnability, your learning rules, your optimizations, how do you handle down batches and do it. So we will be using them as a lot of different examples in order to come down of how a practical network can be trained. So till then we just stay tuned and get back to you later on.